All right, so for number 9, it is very disgusting. It is a very hard problem where you literally have part B worth 7 points. It's pretty crazy and it's pretty disgusting, and it's so disgusting that they would probably serve it at your school cafeteria. Now, all that being said, I'm going to try my best to show you the procedure that comes up to mind as I'm reading, because at the end of the day, that's what I want you to catch on to the most. Understanding the procedure, identifying the important words, the buzzwords, etc., and going from there. See? So, especially in a problem that is incredibly hard and confusing and etc., you gotta go piece by piece. You gotta really dig into the information that they give you, and the best way to accomplish that is thinking in buzzwords, thinking in procedures. So let's see the procedure we have to embark upon this one. So for number 9, we have that an engineer is designing a gutter to catch rainwater from the roof of a house. All right. This fellow engineer knows that the gutter will be open at the top, okay, and is made by folding a piece of sheet that is 45 centimeters wide and 600 centimeters long. And so this sheet of metal gets folded into what we can see over there. See? And so the main idea that we can already sort of notice, and this is actually pretty key, is that this 45 that shows up here, which is going from there to there, okay, is the same 45, just that now it goes from here to here to here to here, right? Like all the way around, basically. See? And so it goes all the way around. All of this is the same 45, just that now, of course, it is folded. Okay? And they also tell us that the cross section of the gutter is shaded in the following diagram. And so I know that a lot of times it can be very confusing by what they mean by cross section, but the big hint that they're giving us is that whatever they're looking for, whether it's cross section or whatever, like smiley face or that part, right? The key is that they tell you that whatever you're looking for, right, is shaded. All right. And so what is shaded in this exercise? Although cross section might seem like a very menacing word, very confusing, we're talking about the shaded part. And so the shaded part is quite literally like just everything that you're seeing. See? And so the cross section is what is considered shaded. It's pretty much this whole diagram. See? They tell us that the height of both vertical sides is 10 centimeters. So if you have 10 over here, that means you have 10 over there. Okay. And that the width of the gutter is W centimeters. See, and so there's a W that goes from here to here. That is my fellow W, which also we can immediately notice if the W is up there, that means you also have a W that goes down here. Okay, this is the same, it's the same W. That it? Because all along the line you have a bunch of W's if you just put them like above or below. And so this W is this, that W up here is the same as this W down there. See? So that's going to be very useful down the line. They also tell us that arc AB, okay, let's establish that an arc is literally like an arcway. See, and so an arcway looks something like this. You have like two pillars, right? And so an arc is going to be this part that I'm putting in green. See? And so the arc AB, which is this guy here, yeah, lies on the circumference of a circle with center O and radius 12. So, because you have a radius 12 over here, right, that means you also have a radius 12 over there. Now, how do you know that? You know that because arc AB lies on the circumference, okay, which is the edge. It lies on the circumference of a circle. And so the full circle, which I'm going to put in like whatever, in green, see? So the full circle would probably go something like this. Okay, this is drawing like very quickly, but point is, because you know that A and B lie on the circumference, and they tell you that you have a radius of 12, and they tell you that from O to B is 12, then you know that the origin from A, I mean, the origin to A, sorry, also has to be 12. See, so from the origin to anywhere on the circumference is 12, and you know that A and B are both on the circumference because A and B are part of the arc. That it? So all of that allows you to fill in your diagram a little bit more nicely, and that's going to help down the road. So notice, we haven't even started the exercise yet, but just by really following the words that they're giving at us, filling in the diagram properly with all the information that they give us, drawing this extra W, putting the 10s, putting the 12s, makes it much more friendly down the road. So especially for these exercises where there's a lot of diagrams and it's sort of meant to throw you off and be confusing, really capitalize on the stuff they give you, put it into your diagram. All information helps. See, especially for exercises that get kind of wild, all information helps. Go piece by piece, make sure it shows up in your diagram. See, make sure everything that you can put in your diagram, you are putting in your diagram. See? So, although it says do not write solutions on this page, we do not care because we are cool kids and I will be writing solutions on this page. So, they tell us to let AOB equal theta radians where theta is between 0 and pi. So, even that, there's a little bit of context I can give you, okay? So, radians, here's the thing. When we're talking about like an angle, see, there's two ways to express how many degrees it has, see? You can either literally say degrees, which is with that symbol, right? Or you can talk about radians, all right? And so here's a little bit of context that I'm sure some of you require. 180 degrees, so 180 degrees equals pi radians. And 360 degrees, okay, equals 2 pi radians. And so notice this pi symbol is not radians, okay? What we're saying is that pi radians, so basically 3.141 radians, is roughly 180 degrees, okay? Guys, this is no different than if you're going from centimeters to meters, okay? Or from meters to centimeters. It's just different units for expressing the same thing, see? And so in this context, they give it to us in radians, which is relatively useful because our formulas, actually, are in radians, right? And so here they also tell you that this angle of AOB, so this guy here, see, has to be between 0 and pi radians, which is the same as if they told you that this angle has to be between 0 degrees and 180 degrees. Right, so maybe that makes it a little bit more friendly. But again, don't be scared when they talk about radians. It's just a way to express an angle. See, we're very used to hearing it in degrees, but well, they gave it to us in radians because whatever, they want to be cool or something. See? All right, jokes aside, it can be very useful to have it in radians, and we're about to see how. So, that is all the context I'm going to give you for now. For part A, we need to show that. So this is interesting. Whenever you have a show that exercise, then that means this is true, okay? So even if you don't do part A, you can still solve parts B and C, knowing that that angle is 2.08. See? So even if you don't figure out part A, you can use the information that that angle has to be 2.08 because this exercise is telling you show that. See? So that is important test taking skills. Whenever you have a show that, take it for granted. It's true. You just have to prove it. And so if in part A you have a show that and part B needs like that angle or needs that result, well, they're giving you the result. So just go ahead and use it. See? So yes, you can skip part A just to do part B in case you're low on time or something like that. It's just a test taking skill tip. All right. So we need to show that that angle is 2.08, correct to 3 significant figures. We will see about that once we reach our answer. See? So for now, how the heck can we prove that angle AOB is theta radians? And so let's focus for a second. AOB, which is the angle that is right here, correct? So this angle AOB is, well, where is it? It is basically like within this sort of arc or sector. Okay, and so here are two important vocabulary words that arise. Okay, on the one hand, if you have a circle, okay, that goes like this, right? So here you have a radius, here you have a radius, and here you have some angle. Okay, on the one hand, you have what we call the length of the arc, which is here in red. See, so this is length of arc. And I mentioned this because it's the kind of stuff that can show up. So this is the length of the arc. And on the other hand, what I'm now putting in, say, pink, okay, and still having this angle as theta, of course. This that I have in pink is the area of a sector, or of the sector, whatever. See, area of sector. I'm just gonna leave it like that. Not in the best English, but I need you to understand that this thing in pink is the area of the sector, and this thing in red is a length. See, so the pink is the area. Okay, pink is area, and what's in red is just the line. It's the length. See, why is this useful? Because the moment that we're looking for angle AOB, you first establish, okay, so AOB, it takes part in the area of the sector, right, and the length of the arc. Because once you establish it's part of a circle and it has to do with the arc and a sector and blah blah blah, maybe you're not too sure how to get the angle, but you know it's part of the circle, you know it's part of an arc, you know it's part of a sector, so you go to the trusty rusty formula booklet. The trusty rusty formula booklet, ladies and gentlemen, I need to establish the following sort of advice. The day of the test, you're gonna walk in with 2 hours of sleep, 2 years of experience, a whole lot of motivation to do well, a whole lot of knowledge that this guy on YouTube and on the internet was telling you, although you shouldn't trust guys on the internet, but, well, I understand you're making an exception for this math channel. Your pen, your pen, your pen, your pen, your pen, your pencil, your eraser, your whatever, okay, your calculator, because it's paper too, and the formula booklet. Guys, you need to get familiar with the formula booklet because it's going to save you the day of the exam and in any mocks or exams that you will ever have for the IB. See, the formula booklet is huge because the day of the exam, you actually go in with it. You actually use it. Okay? And so the formula booklet, you guys, you have to get familiar with it. And once you establish from here that there's an arc going around, that there's a sector going around, well, you go and find that in the formula booklet because you know it's in there. You might not recall exactly where, but eventually you're going to find it, and bada bim, bada boom, here it is. And so on the one hand, here's the length of the arc, which is what I was putting in red, okay? That thing. And the area of the sector, which I was putting in pink, see? So, now that we've established that, okay, so that is why it's useful to know, because you have these two formulas in your formula booklet. Now that we've established that, okay, we can take a good look and see which one is more useful. And so both of them, take a moment, both of them have the theta angle, see? And lo and behold, it's in radians. And so they gave it to us in radians over here as 2.08, see? It's perfect. See, we're just gonna work everything in radians. Forget about the fact that there's degrees at all in this case, see? And so both of them have the angle theta. And so let's see which one is more useful. Well, the one up top gives you the length of the arc. See, so do you have the length of the arc? Can you get it? Is there a way to get this information here? That is the first question, see? And on the other hand, for area of a sector, see, for area of a sector, it's asking for, well, you need the area of the sector, right? So you either, here's the thing, you do have R, okay? And you need either L, which is the length, or area, see? So the moment you plug in R with length, you can get theta alone over here because you have check, check, you're just missing this. Or over here you plug in the radius and the area, check, check, you're only missing this. So you either go for length of the arc or area of the sector. Over here, getting the area of the sector, it's not impossible, but it's, I mean, well, it's a little bit hard. See, you can prove it, there are ways. I think it's a little bit more friendly if you go for length of the arc. I don't want to shut down the idea of doing area of sector, but today I will show length of the arc, see? And so for length of the arc, well, we have to remember the context. And so initially, as I was saying, this sheet metal, which is width of 45, gets folded into this shape, which is the diagram from below, and it's still 45. And so from the context of the problem, you discovered that this part here is 10, that this part here is 10. And so how much does the part in green have to be? The part in green has to be 45 minus 10 gives you this last part in green. See? The length of the arc. And so, of course, that has to be 45 minus 20, 25. See? And so this length of the arc has to be, and let me just try to like leave it a little more clear. So this to here has to be 25. Okay? And so, now for part A, it's much more friendly because you can plug in the formula for length of an arc. So length of an arc is L equals R theta. See? And so from here you can plug in 25, which is the length of the arc, equals 12 times your 2.08. See? Now technically, we need to show that theta is 2.08, so plugging it right now is a little bit troll. And we also need to show that it's correct to three significant figures. So you also need like the OG number, right? And so for now, I'm just going to leave it as theta because we still need to prove it, see? And from here, you can get theta alone. Now to get theta alone, you can divide by 12 on both sides. So this goes away with this. And so theta equals 25 divided by 12, see? And 25 divided by 12, let's check our trusty rusty calculator. 25 divided by 12 gives you 2.08333333. So 2.08333333333333. If I'm not mistaken, yes, that sounds correct. 33333. Anyways, correct to three significant figures. That means you're going to be counting 1, 2, 3, unironically. And then on the third one, you're going to ask yourself, okay, do you round it up or round it down? Do you round it up or keep it the same? And from here, you keep it the same because you would only round it up if it was 5 or above, right? But in this case, it's not 5 or above, so you're going to keep it the same. That means that from here into significant figures, you just leave it as 2.08. Technically, your final answer is 2.08 radians, okay? All right, marvelous. And so that is for part A. For part B, it's the wild one because we're talking about 7 points, see? And so especially for an exercise like this, the cool thing about it is that just doing a little bit can get you like 3 or 4 points very easily, but getting the whole 7 points can be a little bit harder, see? So it's worth looking into this. Don't get so scared by the fact that it's a lot of points. Yes, it's intimidating, and ideally spend your time in an exercise that is a little more friendly or that you know how to face more quickly, right? Use your time wisely, but don't get scared by the fact that it's 7 points, see? A lot of times, it's either impossible or doing a little bit already gives you a lot, see? So think about that, take a good look, see what you can do, see? And so for this part B, you need to find the area, okay, so area of the cross section of the gutter. Now we said earlier that cross section is just the shaded part, see? So basically this is really asking for finding the area of the shaded part, okay? So find the area of the shaded part, which is like just this whole diagram basically, see? Now, for finding the area of something like this, what I suggest is splitting it up into different shapes and going from there, see? And so basically you have a shape that looks like this. Boom, 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 right? And you have some dimensions that go like that, see? And so from here, well, you also know that that is W, right? And that up here, it's not, oh yeah, well, this is also W, see? And so from here, you can really try to consider how to split up this shape into smaller ones and add them up in a wise way to find the area of the whole thing, see? And so if you take a good look and think for a moment, you can start to establish some stuff, see? So some people might be thinking, well, technically I can add like this shape here, and then it's a little bit problematic to try to add this part, like only this part, see? So maybe that idea gets shut down a little bit. Maybe some people take a good look at this and say, maybe I can sort of consider like, I don't know, like making another triangle here and then like adding like these different triangles here and here, right? And trying to go from there. Whatever, guys. There's a lot of different approaches, and if you actually look at the mark scheme, there is like, dude, look at this. There is either this or this or this or there's so many different methods, you guys. That's the other cool thing about these problems that are worth 7 points. There's a ton of different approaches, see? And so I think that the most friendly approach is considering, okay, I can split this up into 3 shapes, okay? Or basically, think about it this way. I'm going to start with 2 shapes, see? On the one hand, you have the shape that is the big rectangle up top, right? So you have the big rectangle that is W, with the tens. See? So on the one hand, you have that shape, right? And so you can do this shape, okay, plus the triangle, okay? So you can do this triangle that I'm putting in dark green, plus the triangle that is light green. I mean, sorry, plus the rectangle that's in light green. So this is 10, this is 10. Technically, over here in dark green, I have a 12 and a 12, right? And so you can also try to find the area of this triangle. See, that you also know that this angle in here is 2.08, right? So you find the area of that rectangle, then you find the area of that triangle, and then you find the area of just the like part of the circle. See? So just the part of the circle, then we can sort of try to solve it. See? And so establishing these smaller goals, these smaller shapes, can make this a lot more friendly to like face. Now, the biggest issue that you might be thinking of right now is like, okay, on the one hand, I need to find W. See, and so how the heck do I find W? How do I do that? Blah, blah, blah. And on the other hand, it's how do you find the area of this? See? And this is why I talked about buzzwords earlier. You know you have in your formula booklet the area of the sector. Now, the thing of the area of the sector is that the area of the sector is technically, right? So the area of the sector is technically what I'm putting in pink, this whole thing there. And so, interesting. So now my game plan can be add the rectangle, right? So first add the rectangle, then add the area of the sector, right? And now from here, as you can see, there's an overlapping area. So this right here is overlapping on both, right? Technically, you're considering this triangle twice. And so what you have to do now, okay, is go ahead and subtract by that triangle, see? Or else you would be counting that area. You would be counting that triangle twice when you add those two shapes, see? And so now my game plan is a lot more like straightforward. I need to consider this rectangle. I need to consider this sector. And I need to consider this triangle, see? So I can add this rectangle with a sector, subtract the triangle, and that will be the area that I'm looking for the shaded part, see? All right, so enough blah blah. Let's try to get into it piece by piece. And so now that I established these different goals, okay, the rectangle, the sector, the triangle, you can go piece by piece and handle one at a time. See? So I'll just go in order, right? And so for the rectangle, you need to find W. And so here you need to use something that no one likes, which is called trigonometry. See? And so technically, right, if you somehow find the W that's in red, it's the same as finding the W that's in black up here, right? They are the same W. And so these dimensions of that triangle, right, I can redraw it for a second. So the dimensions of the triangle are 2.08 in radians, right? This is 12, this is 12, and this is W, see? And so if you want to find W, the tools that you have like force you to need these other two angles, right? And so is there a way to get those other two angles? Now, just so that no one gets lost, why do you need those other two angles? Because of the tools of trigonometry that you have. Basically, you should be thinking trigonometry because I have a triangle, I'm missing a side. How can I get that side? Well, your tools are in trigonometry, which look at that, we're already here. So over here, your main tools are the sine rule and the cosine rule. See? Now, just a quick recap on what these big letters and little letters mean and all that stuff. Angles are big letters. Sides are little letters. See? So if this is big B, that means over there is little c. And if this is big C, that means over there is little c, right? And so basically, I'm just going to literally write it. So little letters are sides, big letters are angles. What is a maybe friendlier way to remember this? Well, notice how here in cosine, you put cosine parentheses, see? And a lot of times we're used to seeing like, I don't know, like sine theta. Well, theta is the global for an angle, yeah? And so you need to make sure that whatever's inside cosine, whatever's inside sine, has to be an angle. And that is why within each of these cosines, you have a big letter. In this sine, you have a big letter, big letter, big letter, big letter. See, so that can be a small hint that, right, the big letters are angles, the little letters are sides. And so basically, for sine rule, okay, you need to consider this. Sine rule works in pairs, okay, because technically, because of these two equal signs, you can look at it like this, okay, or you can look at it like this, or you can look at it like this. See? Let's go ahead and look at it like this, okay? So in this scenario, it works in pairs because look at that. Really what you need is, like following this context, really what you need is side 1 divided by sine of angle 1 equaling side 2 divided by sine of angle 2. And so now that we understand it as like, side 1 with angle 1 and side 2 with angle 2, well, over here, right, you do have this side over there, but you don't have its corresponding angle. And for example, for the 208, you do have this angle, but you don't have the side. And so, if I can just fill in that information, this sine rule suddenly becomes a lot more useful. Now, what I suggest is first try sine rule. If not, go to cosine rule. Okay, so let's first try sine rule. Let's first see if we can get those other two angles. Now, from here, this is the thing. Because these two sides are the same, these two are 12, that means we are in the presence of an isosceles triangle. And so an isosceles triangle, okay, is basically a triangle that has two sides which are the same. See? And so if these two sides are the same, that means that these two angles are also the same. Okay? And so the odd one out would actually be this guy here. See? This guy with that side here would be the odd one out. And so an isosceles triangle, whenever you have two sides that are the same, that means that these two angles that I'm putting in green, for example, if this is x, then this is also x. And so boom, now it gets very interesting because you should know from your math class, at some point you should have learned in this thing called life, that a triangle, okay, if you add up all of its different angles, has to add up to 180 degrees. Now this is in radians, it's not in degrees. Why is that useful? Well, way back earlier in the context part of my explanation, I did mention that, and I think I erased it, lol, but I did mention that 180 degrees is pi radians. So bada bim, bada boom, for finding the angles of x, all you need to do is do this pi, which is basically 180, minus 2.08, which is that angle there. Let me express it in a different way. See, so technically, pi, which is the 180, has to equal 2.08 plus 2x. All right? And so this 180 degrees has to equal that angle plus the other two angles. See, so now it's a little bit more friendly. So from here, you can do minus 2.08, minus 2.08. So pi minus 2.08 has to equal 2x. Now, no one knows how much is pi minus 2.08, so you can put it into your calculator. Pi, which is the symbol right on the clear by pressing the blue. So blue, and then the little thing here, you get the pi symbol. See, so pi minus 2.08 gives you that. See, it gives you 1.06. So 1.061 equals 2x. Divide by 2 to both sides, and I'm going to divide from the calculator, so it's going to be way more accurate than what I'm having on screen, or on the whiteboard, I mean. So divide by 2, boom, there it is. So x equals, look at that, 0.53, and this is all in radians. All right, so now this triangle looks a lot more friendly because now my triangle is, this is 12, this is 12, this is 2.08, this is 0.53, this is 0.53, and boom, this is W. So now you can apply sine rule. Now you can consider all the pairs. And sine rule, sine rule, as I said, was A divided by sine A equals B divided by sine B. See? Now you choose what A is, you choose what B is, in the sense that you pick what is the first angle, what is the first side, what is the second angle, the second side. They just have to be like aligned with each other. They just have to follow the pattern that I mentioned earlier over here. See? So you do have to be consistent, but you choose which one is the first, second, blah, blah, blah. See? All right. So from here, I'm just going to go ahead and say that, okay, so I'm going to have this 12 be associated to the 0.53, right? And so that means I have 12 divided by sine of 0.53 is going to equal w, side w, divided by sine 2.08. See? And so from here, you can just go ahead and cross multiply. So you end up with w times sine of 0.53 has to equal 12 times sine times 2.08. Sine of, sorry, 2.08. Here you can divide both sides by sine of 0.53. So that means that eventually this goes away with this, and you end up with w equals 12 times sine of 2.08 divided by sine of 0.53. Now, before I plug this into the calculator, I will say right away that you do not use sine inverse here because you only use sine inverse if you're trying to get what's inside the parentheses. From here, I'm not trying to get what's inside the parentheses. Sine 0.53 is an actual number. See, so this is the same as dividing by 0.50555 blah blah blah. See? So you only use sine inverse, you guys, if you're trying to get what's inside. For example, if you have, I don't know, sine of theta equals 1/2, and you want to get theta alone, now you do sine inverse, because what the sine inverse does, okay, what the sine inverse does is that this goes away with this. You end up with theta equals sine inverse of 1/2. Okay, that is how the sine inverse works. The sine inverse gets rid of the sine. Here you don't use sine inverse. It's basically just dividing by a number. See? Sine 0.53 is the same as just 0.505533 blah blah blah. See? So there's just a quick sort of reminder of when you use sine inverse or not. But for my value of w, you plug all of this in to your calculator using, your calculator. And what I suggest is putting a fraction. So you can put a fraction using alpha y equals, pressing the first one, and here you can do 12 times my sine of 2.08, all of this being divided by sine of 0.53. And so this gives you your value for w, which is, it's that. See? So your w, I'm just going to put it down here because it's very important what my value of w is. So your w is 20.72582. 582. See? And if you want to do significant figures, you count 1, 2, 3, round it up or keep it the same. You keep it the same. So w, we can leave it more formally as 20.7. Don't forget your units. Centimeters. This is all in centimeters. See? So that is my value for w, and the reason we did it was for finding the area of the rectangle. See? So the area of the rectangle, let's just go ahead and calculate it. It's going to be length times width. So it's going to be 10 times w, which is the same as 10 times 20.07, see? Which is going to give you, well, 207 actually. So quick maths there. I was cooking a little. 207, see? So the area of the rectangle, I'm going to be putting the answer of the areas in, I'll leave it in dark blue, see? So the area of the rectangle is 207 centimeters squared, okay? Now let's go ahead and try the area of the sector, see? And so for area of the sector from the formula booklet, we know that the area of the sector is simply 1/2 times r squared times the theta, which is the angle in between, see? So this one is actually way more straightforward because you know that, well, following that formula, see, we know that the area of the sector, so area sector, okay, equals 1/2 times r squared times theta, see? And so with this context, the area of the sector is just going to be 1/2 times the radius, which we know is 12, so 12 squared, times the 2.08 from part A, see? So all of this in our calculator is way faster than the last calculation we did with the rectangle. See, so this is a lot more friendly. So you do, let me just be organized. You end up with 1/2 times this 12 squared times the 2.08. See? So that gives you around 149.76, 149.76. Technically from here you can count the three significant figures. So you can count 1, 2, 3. Do you round it up or keep it the same? You round it up. And so the area of the sector, we're going to leave it as 150 centimeters squared. See? And now for area of a triangle, well, you do have the same triangles from up here, see? So finding W was very important. We know that W is 20.7, see? And so if you redraw that triangle with all the stuff that you know now, which is very filled in, see? You have this 2.08, you have this 12, you have this 12, you have the 20.7, and here you have, what was it? 0.53? Yes, you have 0.53, and you have 0.53, see? All right, awesome, beautiful, nice. And so how do you find the area of this? See? Well, on the one hand, you can try to find the height, okay? And you can do that by splitting the triangle in two and splitting that angle in two and a bunch and splitting this in two as well. Like you probably saw that. It's like the most like typical way to do it. See? But I do want you to open your eyes to the new formulas in the formula booklet. There was a new patch note and they added nah, just kidding. There's always been area of a triangle. See? And so actually, and this is important to know, see, for area of a triangle, technically you have two. And so you have this one, which is like the trig version, and this one, which is the OG. And so the OG is base times height divided by 2, which is why you would try to split this in half and all that stuff. See? That way you find the height, you find the area of half a triangle, then you add it to the other one, it's the same triangle. Yeah, that's one way to do it. It's the classic. See? But I do want you to start noticing because for some exercises in the B, I've noticed you like have to do it this way. See? Not in this case, but I want you to start training your eye for it. See? This area of a triangle also works. See? It's going to give you the same answer. They both work. Let's really understand what it's asking for. See? So as I established earlier, the little letters are sides and the big letters are angles. And so here, I'm going to like simplify it for you a little bit. See? All you really need is an angle and the sides next to it. And the sides next to it. See? And so if you like really get this into your brain, because this formula is amazing. See? For a lot of exercises, it makes it go so much faster. And for a lot of exercises, you have to use it actually. See? So on the one hand, I'm really establishing that, dude, there are two formulas for area of a triangle. Do not forget. And also, this one on the bottom, the IB loves to put it in there because a lot of people don't review correctly, don't study with the formula booklet, but you will because this guy on the internet is telling you to. So once you do and you understand that this second formula, all it really needs is one angle and the sides that are next to it. Well, now you can find the area of almost any triangle because all you really need now is, I'm going to draw the same triangle 3 times. See? So you can find the area of the triangle if you have this angle and those sides. You can find the area of the triangle if you have this angle and those sides. And you can find the area of the triangle if you have this angle and those sides. See? That is all that this sine rule is asking for. See? And so if you go all the way over here, well, you have the whole triangle. So you can use like pretty much anything. But the most direct approach, or what you probably would have ended up doing, is thinking of it like this. See? And so from here, the area of the triangle, following the formula booklet, is 1/2 times AB times sine C. See? But as I established earlier, it's just an angle and the sides next to it. So think about it this way. First, I'm going to put the 1/2. I'm not going to put A and B yet, but I will put sine of, say, 2.08. See? So what are the sides next to angle 2.08? Well, it's the 12 on the 12. So A and B are both going to be 12 and 12. So bada bing, bada boom, put all of that into your calculator, and you will find the area of the triangle. So 1/2 times 12 times 12 times sine of 2.08. So when you look at that, that is the angle of our triangle. Let me just put it in blue over here. 62.86. 62, actually, let me redraw that for a second. So the area of the triangle that we just found was 62.8655, right? And to three significant figures, you count 1, 2, 3, round it up or keep it the same. You round it up. And so the area of the triangle here is 62.9, technically. See? And so from here, we just follow the process that we initially mentioned. We will be adding the rectangle in the sector and subtracting the triangle once because we don't want to count the triangle twice, right? If you add the rectangle and add the sector, you're adding this part of the portion twice on both, see? So you want to get rid of it at least once or else you're counting two triangles. That's not what you want to do. And so from here, let's go ahead and do the 207 plus the 150 minus the 62.9. That gives you 294.1. And so the area of this cross section is 294.1. You count it to significant figures. You can say 1, 2, 3. Round it up or keep it the same. You keep it the same. So really, the area or your final answer is 294 centimeters squared. See? And so for part B, it was a long and hard-fought 7 points, but there it is. And so the area is going to be 294 centimeters squared. See, and just to show you guys, here it should be on the mark scheme right over there. There's the 294. See? So 294, don't forget your units, centimeters squared. See? And last but not least, you guys, we have that in a storm, okay, we have this whole other part of the problem. See, it's kind of wild, but take it easy. It's more straightforward than what you think. See, I think the hard part was part B. Part C is tough in terms of thinking about it, but the math behind it is actually, you're going to notice it's very easy. See? So in a storm, the total volume, okay, so suddenly, we're talking about volumes, right? So the total volume in centimeters cubed of rainwater that enters the gutter can be modeled by a function RT, where T is time, all right, this might be relevant, so T is time since the start of the storm. It was determined that the buzzword, they even put it in bold for you, so the rate at which the rainwater entered the gutter could be modeled by this guy here, see? And so why is this relevant? Well, take a small look, see? Up here, they're talking about the function RT, and down here, they give you the derivative version. See, let's recall that RT like this is like the original, that this is the derivative version, and that this is the inverse with the -1. See? And so in this case, we're talking about the derivative version of it, which is why we're talking about rate. See? Remember that the derivative version of it basically gives you slope, which is the same as talking about rate. Okay? So enough blah blah. The derivative version, see, so careful, the derivative version of this, all right, is that formula that shows up right here. See? The other piece of information that they give you is that t has to be greater than or equal to 0. This is pretty standard. On the one hand, it's telling you the domain. Okay, so it's telling you that your values of t can only be greater than or equal to 0. But it's also pretty standard because we're talking about time. So it's pretty common that time is going to be 0 or greater and not like negative. So you're not going to go back in time. It's just 0, like positive time. It's just positive time. So your value of t basically just has to be positive. All right. And look at this. During any 60-second period, if the volume of rainwater entering the gutter is greater than the volume of the gutter, it will overflow, which makes a lot of sense. Like if you have like a cup of coffee, you have a cup, see, and you put it outside and it's raining, see. If it's raining like hard enough, the cup is gonna fill, see. Now imagine that you have the same cup, but it has a small hole in it, see. But the hole is very, very small, see. So you have a cup, ¿vale? And it has a small like hole in it, okay? Just a small, small hole, see. And so if it's raining, ¿vale? If it's raining into the cup, it's gonna fill out, but it's also gonna come out a little bit, see. And so basically what it's saying here is that on the one hand, careful with how much comes out of the gutter or the cup or whatever, and on the other hand, careful with how fast the rain is entering, see. And so basically the big question that they're trying to ask you here is, will it overflow or not, right? Another way to think about it is, will the volume of the water be greater than the volume of the gutter, which is really just pretty much mansplaining because it's what it's saying over there. See? So, will the volume of the water be greater than the volume of the gutter? That is the big question. See? And so for part C, that's literally what they ask for. For part C, it's determine whether the gutters overflowed in the storm. Justify your answer. See? And you need to analyze this thinking in 60-second periods. That it? So, definitely a little bit more of an exciting part of the problem, but it's also easy points if you know what you're doing. See, so these are 5 points that should go by flying, and you're really going to notice how. So on the one hand, you can get a bunch of points by first finding the volume of the gutter, the volume of the gutter. So for part B, you found the area of the gutter. See? You found that the area of the gutter was 296 or 94? 294. See? So the area of the gutter is 294. So what is the volume of the gutter? Well, think about it this way. See? If you have a rectangle that goes, I don't know, 12 and 20, see? The area of this is just going to be 12 times 20, right? And so the area of that, so area is 240. Got it? And if suddenly someone comes by and says, let's stretch it out a little bit, see? And so if they go ahead and stretch it out a little bit, what you're going to end up with is, and let's say that they stretch it out by 5, see? So in this direction, it stretches out 5, right? And so that means that for calculating the volume, right, and maybe I should have written this down, the calculation for area we said was 12 times 20. Well, the calculation for volume of a cube, or like some prism like this, is really just 12 times 20 times 5. And so basically, you can also think about it this way. For calculating volume, it's like the OG area times how much it extends. And so really keeping this in mind is huge because you have the OG area. Now you just need to see it by how much it extends, right? And so for the volume of gutter, it's going to be the 294 times by how much it extends. And way back earlier, well, by how much does it extend? See? So go ahead, review everything, read what you have. This is one of those crazy exercises where they give you a ton of information and boom. At some point they did say that the gutter is 600 centimeters long. And so you take the area of this guy and you multiply it by the 600 in order to get the volume of the whole thing. See? And so suddenly it makes a lot more sense what the approach has to be. For the volume, you're just going to do the 294 times the 600. See? And the main concept I need to explain is this guy here. All right, so volume is always going to be the original area times how much it extends for a shape like this one. See, if you're talking about a pyramid, it would be different because it has like these edges that go inward and stuff like this. But really, this is just, I mean, it makes sense, right? The cube like just extends backwards by 5, so you multiply by 5. See? Over here, well, you have this shape over there, but the shape over here appears like a bunch of times. How many times does it appear? It appears 600 times. Quite literally. See? So, that is a sort of concept that once you have in mind, finding the volume is really easy. The volume of the gutter is just going to be 294 times 600. See, so the volume of the gutter is giving me actually a nice number. So volume, I'm going to put volume gutter, okay, equals 176, 400. All right. So boom, that is already a couple points in the mark scheme, as you can see here. The volume of the gutter is like the first step that you need to do, right? Here, there's going to be a couple different answers because it depended on your method, depended on using significant figures or decimal values. But don't worry, over here it tells us that multiplying 600 by your area is good enough. See? So, once we establish that the volume of the gutter is 176,400 centimeters cubed, okay, now you need to try to find the volume of the water or of the rainwater. See? And so think about it this way, right? This is the intuition that I'm going to really try to like embed upon you. So right now you have a function for rate. See? Now, we are talking about the volume of the rainwater in a 60-second period. And so technically, if you find the rate, right, in the first second, and then the rate in the second, and then the rate in the third second, right, and all the way until reaching the rate of the 60th second, right, if you add all of these together, then it's like you're basically calculating how much water entered the first second, how much water entered the second, the third second, the 60th second, add all of those together, and that gives you the total volume, right? Now, I'm sure there's at least one of you thinking out there, but what about the rate at second 0.5? What about the rate of second 2.2? What about the rate of second 4.20? So, if you want to add all of those rates and everything in between, you have to use the integral. See? And I'm going to write it like this because technically the integral, that's what it does. Okay? It takes like an interval and finds you like the sum of all that stuff. See? Usually you use this for volume or stuff like that. See? So generally it's used for volume, but the main idea is that you have an interval. Okay? You want to add like the derivative of that within that interval like 60 times, see? But really it's from 0 to 60 more than 60 times. And so you should be thinking in intervals, see? So once you establish that that is an appropriate approach, what you can do is, well, write the integral. And so the integral would be the integral from 0 to 60, right? And so let's first talk about that. You put a 0 down here because it's your like first x value, and a 60 up there because it's your last x value. Now, why is this the case? Because we are talking about a 60-second period. And so on the one hand, that's the first thing you need to establish, right? This is the integral from 0 to 60 because we're talking about 60-second periods. And, well, you're doing the derivative of your function, right? So technically, you're doing the derivative of your function, which is just going to be 50 cosine 2 pi t divided by 5 plus 3000. And so if you solve this integral here, and what are you doing in respects to? You're doing it in respects to dt, right? That's going to give you the volume of the rainwater, see? And so how the heck can you do that? Well, you can do it by hand and go crazy, or you can use your graphing calculator. And so here's a little bit of a magic trick that I'm going to show you. You can solve integrals with your calculator, see? So how the heck do you do that? Well, you probably should know by now, if you watch some of my videos, that if you press alpha y equals, it shows up for fractions, see? Usually we just use the first one and forget about it, but really, take a good look. You have fraction column over here, the function, the matrix, and the y var. And so in this version of my calculator, I can travel through them. Maybe you can't, and if you can't, all you need to do is press alpha and window to open the second column, see? And so we want the second column because over here you have f and int, and all it's really telling you is that this is the function of the integral. So boom, you press it, there's my integral. Look at that, it's beautiful. It's beautiful. It's crazy how much this calculator can do. So here you plug in 0, here you plug in the 60, and here you plug in your whole function. And so just be careful, plug in carefully, take your time, don't get too excited. Use everything you've learned to not mess it up. Basically, just take your time, see? Instead of putting t, well, I'm not too sure if you can like name a variable t here, but we're just gonna put x. See, it works. It'll do whatever. See, so we're just gonna put x down here. Down here we are going to put 5, close parentheses, plus 3000, and all of this in respects to x. We know it's really t, but just put it like that. Press enter. Pray that your calculator doesn't explode because it does take a little bit to calculate it, but eventually, bada bing bada boom, you end up with boom, 180,000. And so the volume of the rainwater is 180,000. Now, guys, now you need to do the conclusion. I think it's pretty straightforward. So, the volume of the rainwater is 180,000. The volume of the gutter is 176,400. So, which volume is greater? Volume rainwater is greater than volume gutter. Okay? Another way you can sort of get the method point is literally putting that 180,000 is greater than 176,400, right? And through this, your conclusion is that it does overflow. Okay? It does overflow, unfortunately. And ladies and gentlemen, that is your procedure that we will be doing for number 9. So number 9 was pretty wild. It had a lot of stuff associated to it. It was probably a long monologue at some points, but I think it's important to explain things from zero just so that everyone understands. There were quite a few concepts that I had to go over, so, well, that is number 9. Number 9 is wild, you guys. Okay, number 9 is not easy. If you looked at it and you were like, damn, what the heck? Trust me, I thought the same, okay? Number 9 is pretty wild, but once you understand these keywords like, we're talking about volume and they give us rates, so you're thinking of integral, right? Or for example, you have this show that, so like you can sort of relax that, like, okay, you don't have to do part A in order to get B and part C. That also is a good test taking strategy. Or, the moment that you split up this shaded area into a bunch of smaller shapes makes it a lot more friendly, right? Stuff like that is what helps you help yourself. See, at the end of the day, you guys, I'm just giving you tools so that you can help yourself better. Okay, that is my true sort of goal here and what I'm going for. And if it makes you do better in the IP, then we're all happier. See, so ladies and gentlemen, that is for number 9. I'll see you around, and I hope it helped. See ya.